I'd be dunking, I'd be out there doing everything. I don't know. All right, guys. This is a little bit longer. We'll spend probably a day and a half looking at this. For our next sort of step into the world of what we do with these derivatives, right? So far, Lexi has mastered the concept that critical points do important things. Most specifically, they give us information about where potential extrema occur, right? Now, guys, here's a visual for you, okay? If I need to get here, right? If I need to get here, and would you say relative to the other desks, this would be a maximum? Fair to say, because it's at the same level, right? So they would all be maximums, right? But I'm down here right now, right? So if my feet represent a point, for me to get from here to there, I gotta climb, right? Okay, so what is my change? Give me a word. Going up, increasing, rising. Give me one more word. Say again. Yeah, yes. Elevating. Positive. Right? Okay. Now, if I'm at a maximum, the only place I can go back down. What am I doing? Negative. Decreasing, right? Stepping down. So guys, in order for me to get to a maximum, what must I have done? Increased. But it's not a maximum unless I did what afterwards? Decreased. Right?
Is that why you can't have an endpoint? Because you're not doing anything.
Right. So, right, for me to get to a maximum, I have to increase, then decrease. For me to get to a minimum, I have to decrease and then increase. Fair to say? Mm-hmm. All right. Well, guys, we literally just talked about the entire lesson. Because now, when I ask you where something is increasing, you said something is increasing when it's rising, positive, the rate of change is growing. In other words, the derivative is greater than 0. So I'm increasing when the derivative is greater than 0. I'm decreasing when the derivative is less than 0, right? And I'm at a constant rate when the derivative equals 0. Okay. And that's what everything here basically has. If you look at this graph is increasing for a couple of different reasons. One reason is as you move and x values increase, y values increase, and tangents are positive. Tangents are negative, tangents are equal to 0. Everybody agrees with that. So if I look at this graph, where is this graph increasing? Well, would you agree from here to here? Why is that increasing, guys? Because as I move left to right, the y values are getting larger. Also because any tangent drawn to this curve from here to here would be positive. Do I include the endpoints? No. So I am increasing from -3 to 1. Where am I decreasing? Well, what am I doing from here to here? Constant, right? Yeah, so from 1 to 3, I was constant. Because what? The y values didn't change at all. And then from 3 to 5, I was decreasing. Okay? Guys, if a function is monotonic, Evan, monotonic, then the function is always increasing, decreasing, or constant. In other words, that would be monotonic because I am always what? I'm always rising, right? Are there any minimums on this curve? No, right? No, there's no minimums. So if there's no minimums, I must have not been decreasing at all, right? So I'm always increasing. If I did this, I would be always decreasing, okay? As soon as I did this, I'm no longer monotonic because I have a what? I have a minimum, right? I have a minimum, which means I must have been decreasing at some value, okay? So I'll use that phrase monotonic. And we've actually, I think, used that phrase monotonic before. All right. Guys, I already did this visually. Lexi, I said if I have a continuous function, derivatives occur at critical values. If I have a discontinuous function, derivatives have critical values at discontinuity. We already know that, right? In other words, what? Derivative of the numerator, derivative of the denominator, those two things give me critical values. So here's what I want to do. I now want to know, where is this thing increasing or decreasing? Okay. Now, what could we do? Well, we could absolutely, no doubt about it, graph it. Yes? Take out our calculator, let's be on our way. How could I do it? Using calculus. Well, in order for it to be increasing or decreasing, I had to have hit a critical value. Yes? So let's figure out where those critical values are. So we're going to take our derivative. All right, so there's my derivative. And what do I know about the derivative? The derivative gives me critical values when it equals 0 or doesn't exist. All right, so at 0 and 1, I have some critical values. Do we know what this looks like graphically? What would this look like graphically? It would be a parabola with roots at 0 and 1, right? Okay. So I'm going to give you a sketch of the derivative, right? That's a sketch of the derivative. No doubt about it. Okay, ready? Now this is where I'm going to confuse you. I guarantee it. So this is where you really got to be with me. This is a sketch of the derivative, right? If the derivative is greater than 0, what did we say about the graph? It's increasing. When the derivative is greater than 0, I'm increasing, right? We said that when the derivative is less than 0, I'm decreasing. Hey guys, where am I when the derivative equals 0? Don't say at 0. I don't really want to know where. I want to know at what in between, okay? Guys, what does the derivative equals 0 mean? It's a critical value, right? And what are critical values again? Could be endpoints. Does this one have endpoints? No. Or the derivative equals 0, which means you're at a
Constant.
extrema, which is a max or a min. Yes. Okay. There you go. So it took us a while to get there, but this means I'm at some maximum or minimum. Also remember that what? We also have this possibility. Actually, hang on a minute. Do me this favor, guys. Write max, min, possibility. And we'll talk about what that means in a minute. And we also know that the other option is that what? This does not exist, right? So those are all of our critical value analysis tools, right? My derivative is greater than 0, I'm increasing. Derivative less than 0, I'm decreasing. Derivative equals 0, I'm at a possible max or min. And then when the derivative doesn't exist, that's another possible critical value, right? Okay, so these are all of my things. Now, again, guys, listen carefully. This is a graph of my derivative. Where is this graph greater than 0? Here and here, right? Where is this graph less than 0? All of that. So where do I have maximum or minimum possibilities? Here and here. So when I say f prime greater than 0, I'm talking about y values, right? Okay. So for this particular example, guys, I'm increasing on the following intervals. Ready? Well, increasing is the yellow portion, right? So would you agree it's from negative infinity to 0? And from 1 to infinity. So that's the idea of using interval notation, just looking along your number line, right? So I'm just looking along this axis. Would you agree I'm decreasing between 0 and 1? And we'll talk more about the maxes and the min possibilities in a minute. But right now, this is all I really wanted to know, right? Okay. So again, what did I do, guys? Took my derivative, right? Made a quick little sketch, looked at a visual of what the derivative is, and analyzed it that way. Evan, that cool so far? All right. I'm not going to read through all this. I'm gonna do this example, and then we're going to come back and go through it, okay? All right, so here's what your first derivative test is going to do. Ready? And that's, guys, we just did a first derivative test. A first derivative is going to tell you if you have possible local maxes or mins based on increasing and decreasing values. Check this out. Ready? Guys, I want you to use the following words. Increasing, decreasing, maximum, minimum. Ready? Go. Okay. Again, increasing, maximum, decreasing. Okay. Same words. Ready? Okay. Do you guys agree that the minimum occurred after I decreased and then increased? Okay, now check it out. Ready? So let's pretend for a minute that the derivative at this one point was 0. Let's pretend that it got really flat. Would that have given me a critical value? It would have, yes. But here's the problem. A critical value does not guarantee me what? A maximum or a minimum. It only guarantees me a maximum or minimum if I what? Switched from increasing to decreasing or decreasing to increasing. Because if you look at this right here, I'm increasing, 0, increasing. But I didn't have a max or a min, did I? Same argument here, right? So that's what this stuff right here basically describes. The only way I can have a maximum or a minimum is if I have a critical value and I change from increasing to decreasing or vice versa.
Wait, so if a limit is like not the same, it isn't, or if a limit at a point isn't the same,
Yeah.
it's a maximum or a minimum.
I don't know how limits got into this.
Yeah, I don't know either.
Yeah. Don't think limits.
Okay.
Yeah. Don't think limits. I think I see where you're going, and I think we're actually going to do something similar to what I think you're asking me at the end of this lesson. I'm pretty sure.
Okay.
All right. So, ready? We got this guy. What do I want to know about this guy? I want to know where is it increasing and decreasing. So the only thing I care about is the derivative and knowing where that derivative is greater than 0 and less than 0. Simple derivative to take, no problem. Simple derivative to take. But now we go to algebra class. Because what do I want to know about that function? I want to know where it's greater than 0 and less than 0, and I can't really figure that out unless I know where it's equal to 0. Yeah, so let's figure out what our critical values are. Going to take out an x squared. It's going to give me that. I'm a super awesome factorer. So I know that I get this. And I get this. Yeah, that should be 4. Sorry. There we go. Like I said, I'm a super awesome factorer. All right, set those equal to 0, and what do we get? We get 0, we get negative 1/2, and we get 4. Right?
Oh, never mind.
You good?
Yeah, I put the 2x in there.
Now, again, all I want to know is what? Increasing, decreasing. I'm going to do a sign analysis now. And this is the process you guys are going to want to use. We know that on my number line, or my x-axis, right, lies the following things. Negative infinity and positive infinity. This root, and this root. So, guys, I know again that if I were to graph this, right, that I'm going to have some 4th degree polynomial that has this root, and this root, right? Really, really important thing to talk about now. I like doing sign analysis. Give me a number, guys, that is less than negative 1/2. Negative 1. Give me a number that is between negative 1/2 and 0. Negative 1/4. A number between 0 and 4. 1. And a number bigger than 4. 10, sure. So what I'm going to do now is I'm going to really quickly plug these in. to figure out what I get. Any negative number to the fourth is what? Positive. This is going to wind up being negative, but I'm multiplying it by a negative, so it's going to wind up being positive. This is going to be a positive, but it's going to wind up being negative, so oh crap, I do got to plug it in now. Okay, so what if I plugged in negative a bajillion? What's negative a bajillion to the fourth? Some big positive number, right? So does any of this matter after that? No, this is going to be positive. Okay. What if I plugged in negative 1/4? Well, oh geez Louise, that's going to be some small decimal. It's going to wind up being what? 2 over 256, so almost 0. This is going to be an odd small decimal. This is going to be positive. Okay, small number again. This is going to be something, but then it's going to be -4. Okay, so what am I trying to illustrate here? First of all, plugging in these things is kind of a pain, right? Agreed? Okay, which is one of the reasons why, do you remember back in pre-calc, you talked about a couple of things that were important, one of which was end behavior? Well, talk to me about the end behavior of this graph. It's 2x to the fourth. They're both going to go positive, right? They're both going to do this. So I know my graph is going to do this and this. So I got to connect to those eventually. Guys, do you also know what the y-intercept is of this? What's the y-intercept? What am I adding to it? What constant? 0, yeah. Okay, so I have that. Okay, it's also a root, by the way, right? So be it. And then one other thing, guys, that's really important, and you probably forgot about this. I guarantee you did. Because what you're trying to do right now in your head, I guarantee it, is play connect the dots. And the problem is, if I try to play connect the dots, what happened? I have no more what? I have no more root to get up to here, right? So what you had to recall is the fact that what? This factor is a double factor. And what do you know about double factors? They bounce. They bounce off the axis. Yeah. So you have a double at 0, which means when you're playing connect the dots, it's just going to bounce off of it and then do that. So that's what your graph of again, what's that the graph of, guys? That's the derivative, right? Now, if you did your sign analysis, guys, if you did your sign analysis, this would have been a negative number, this would have been a negative number, and this would have been a positive number if you plug them in. Just like the what? Position of the curve. All right, so where is this increasing? Well, it's increasing when I'm here. So that's going to be what? From negative infinity to negative a half, and from 4 to infinity. And then where is this decreasing? Well, it's decreasing here. Boom, boom. How do I write that one? That's kind of a tougher one to write. How do I write that one? It starts at negative a half and goes to 0. So I write starts at negative a half, goes to 0, and then picks up again at 0 until it gets to 4. So decreasing. Okay. Now, this next one, guys, I guarantee you, there's no question about it. I would bet my job on it. You're going to have to write this exact phrase at least once on your AP exam. I guarantee it. There's no question about it. Okay? And the exact phrase is this. determine the x values of any local maximums or minimums. So Evan is going to look along this curve and he's going to say, did this ever go from yellow to blue or blue to yellow? Where did that happen? Half? Or negative a half, yep, and 4. Why not here? It was blue the whole time. It was what? Decreasing and decreasing. So I didn't have a what? Change from increase to decrease or decrease to increase, right? So what I'm going to say is this. F of x has a minimum at, okay, so where's the minimum? I'm increasing, decreasing, increasing. This is the derivative. Oh, good. Oh, I'm so glad that you just asked that question. Everything we're talking about is about what? This, right? Everything that we're doing, all of this work is so that we can describe what this looks like. Agreed? Yeah. So where does this have a minimum? Well, this has a minimum when this stopped decreasing and started increasing. So I had a minimum at 4. Because the derivative changed from negative to positive at x equals 4. And then what am I going to say? I'm going to say the opposite statement for what? For the maximum. And where did the maximum occur? Well, what am I doing? I'm increasing, 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 and then I'm decreasing. So this must have been the maximum. So the maximum occurs at that. All right, and guys, that becomes like super, super important right there. That concept right there becomes super, super important. How we doing? All right, now we're going to do it without any graph at all, okay? And this will be the last one we'll do today. No graph at all, guys, right? Give me any relative extrema. Give me any okay, so I'm asking for relatives, so I'm asking for locals, right? That's good. And I want to do it on this interval. Relative extrema on an interval. Good. That sounds like something we can do, right? I got a beginning, I got an ending. Relative extrema could occur at these endpoints, right? So we'll check those. We'll check those. Oh, could they? Oh, hang on a minute. Relative extrema. Do local maxes and mins occur at endpoints? No. Okay, so we actually won't check those. All right, so let's figure out what we got here. What's our derivative? Derivative is a half minus cosine of x.
we want to see if we have any critical values. So where is that equal to 0? And where is x equal to 1/2 on a cosine curve? From 0 to 2 pi. Uh-huh. Okay, good. So let's go with that. 60 degrees. She's right, 60 degrees. Give me 60 as radians now. Pi over 3. All right, and then ASTC, right? So cosine puts me into which quadrant? Yeah, because I got to be positive, right? So I got to be in this quadrant here. And then, Lexi, if pi over 3 is my reference angle, this would be pi, right? So that would be 3 pi over 3, right? So if I continue to go around to here, this would be 6 pi over 3 to make it 2 pi, right? So if I take 6 pi over 3 and I go back one reference angle, where am I? 5 pi over 3, yeah. Your other option is just use your 60, go to 360, subtract it, and then convert to radians. All right, so what does that mean? How many critical values? 2 critical values, right? Okay, so now what do I have? I have, again, I said I'm going to do this whole thing, what? Without a graph, right? I'm going to do the whole thing without a graph. So I'm just going to create a number line, put my endpoints. And I'm going to put those. All right, so guys, give me any value between 0 and pi over 3. Make it something that I can easily plug into this.
Pi over 6.
Pi over 6. Pi over 6 is definitely smaller than pi over 3. Give me something in that middle. Make it even easier than that. Pi. 3 pi over 3. And then how about, can we do 7 pi over 6? Or no, that's too much. 5 pi over 6. No, 11 pi over 6. There we go. 11 pi over 6. All right, so pi over 6 is what? 30 degrees, right? Okay, so what is cosine of 30? Radical 3 over 2. What's 1/2 minus radical 3 over 2? Radical 3 over 2 is what? 0.86? 0.866 or 0.886? So this is 1/2 minus that. It's definitely a negative number, right? Okay, what if I plugged in pi? What's cosine of pi? Cosine of 180? -1. What's 1/2 minus -1? 1/2 minus -1. Positive. And guys, 11 pi over 6, isn't that going to give me the same thing as pi over 6? It's going to give me another negative. Okay, so check it out. Ready? And this is what's kind of cool about this now, right? What did I do? Ready? 18. On my graph, this is negative, so I'm decreasing, decreasing, decreasing. Then I'm increasing, increasing, increasing. Then I'm decreasing, decreasing, decreasing. So I know that it probably had what? Potential maxes or mins here and here, right? So if I went from decreasing to increasing, what must this have been? A minimum. I went from decreasing to increasing. So this must have been a minimum. So since, this is another way you could write what I did on the previous page. Since f prime of x goes from negative to positive at x equals pi over 3 x equals pi over 3 must be a minimum. And then what do? Then I go from increasing to decreasing. So if I go from increasing to decreasing, 5 pi over 3 must have been a maximum. And then so 5 pi over 3 must be a maximum. What do you think? What do you think? Feedback? Questions? Yeah. Okay, we're doing okay? All right. So guys, if we look at what we're going to do here in the next pieces of this, find the relative extrema, right? So all I want to know, are there any maxes or mins, right? And that's going to be using something that's a little bit more of a complex derivative, right? Find the relative extrema. Just going to be what? A little bit more complex derivatives. And then I think, Emma, I think this might have been what you were talking about. So we'll look at a weird case of a piecewise function and talk about some simple ways to analyze this. And then these ones as well, where we actually, we analyze them, but weird things happens because, hang on, guys, look at this function. What do I know right now? Where do I know there can't be any potential maxes or mins or anything else? 0, right? So like that changes the game a little bit, only in that you got to make sure that when you give your analysis, you take that into consideration, right? So that's where we're going, okay?